Yeah, so hello everyone. Virtual string seminar. Today we are happy to have Suresh from Madras, and his talk is titled of Lie Algebra using counting dyon. Over to you, Suresh.
Thank you very much for the kind invitation. And this was a very difficult talk to prepare because it falls somewhere between maths and physics, somewhere bang in the middle. So neither a mathematician nor a physicist will be able to be at home with what I'm going to do. So what I've done is try to, spend more time explaining things rather than focusing on my results. The details you can get from this paper, which just came up in June. And this is work with my PhD student, Shabir from IMSc, and a mathematician from IMSc, Vishwanath. And so let me get started now. So the introduction is going to be fairly long, and then I will be ready to understand the statement of the problem. And then I will just show you our key idea, which is how to embed an affine into a class of Lie algebras that we are looking for. And then I'll just go ahead and discuss what we are looking ahead for. Okay, so one thing I want to emphasize is that I'm saying looking for a new kind of Lie algebra. We have not found it yet. We have the seeds of what is in it, but we don't know the complete answer. So this is actually work in progress in that sense. So we start with the physical introduction, and then there will be a mathematical introduction. And one more thing is I allow interruptions of any kind, and no question is stupid, no question. So everything is accepted. So the simplest example of n equal to 4 string theories in 4 dimensions is obtained by compactifying type 2a or type 2b string theory on K3 cross T2. That's the third way of doing the same thing by taking a periodic string, the spelling mistake here, compactified on T6. And actually, in 6 dimensions itself, there's a triality between type 2a or b on K3 and heterotic on T6. So this triality descends to 4 dimensions. And this theory has n equal to 4 supersymmetry, which is 16 supercharges if you count it up. So in 4-dimensional supersymmetry language, it's n equal to 4. But here is a simple way of understanding 16 supercharges. And the point is that this is very esoteric, and more realistic ones would be, with lesser supersymmetry or even no supersymmetry. And so in this theory, the electric and magnetic charges are objects which are valued in an even self-dual lattice of signature 6, 22. And there are 2 symmetries. One is the perturbative, which is usually called T-duality, which is SO6, 22Z, which is automorphisms of L. So you have a lattice L in this Lorentzian, in this space with funny signature. And it's a subgroup of SO6, 22R, which maps the lattice to itself, and that's the T-duality group. And PSL2Z is the S duality group of symmetries, which contains, electric magnetic duality sitting inside that thing. So the electric and magnetic charges here, QE and QM, are vectors, if you wish, of 28-dimensional vectors, each transformed as vectors under the T duality group. And the quantization is such that half, so QE square means QE dot QE. So half QE square is one integer, and then QE dot QM is also a second integer, and m, which is half qm square, which is also a second integer. So these are now T-duality invariants, but they are not invariant under PSL2Z or SL2Z, which is electric magnetic duality, for instance. And so you can see under electric and magnetic duality, N and M will get exchanged, and L will go to itself. Okay, so they transform as a triplet under PSL2Z. So in these theories, we can talk of counting of half BPS states. So half BPS states are states which preserve half of the 16 supercharges. So 8 are broken and 8 are unbroken. And the multiplet, the BPS multiplet will be 2 power 8 by 2, which is 16. Okay, so this is that 16 up here. And so we are interested is say in only electrically charged black hole, not necessarily black holes. So I will call them BPS states because for low charges, these are not black holes. And so for large charges, they might be. Okay. So let D of n denote the microscopic degeneracy of electrically charged half BPS states with charge given by half Q e square equal to n. So Qm is 0 in these cases. And but by the way, I mean, you can have half BPS states which have both electric and magnetic charge. And so let me just remind people what a dyon is. Dyon is something which carries both electric and magnetic charge. Okay. But we are looking at a special case of what is called electrically charged, and there's a convention involved. Okay, so it turns out that that is generated by some special function called the degenerator function, and it's to its 24th power. Okay, so this is so that gives this degeneracy, and the simplest way to understand this is that there is some duality frame in which these half BPS states get mapped to states of a heterotic string. Similarly, if you have dionic, that means it is electric and magnetic charges. So quarter BPS are necessarily dionic. If it's pure electric or pure magnetic, it is necessarily half BPS. And so here now, when we say quarter BPS, quarter of 16 is 4. So 4 supercharges are not broken and 12 are broken. So 2 power 12 by 2 is 64, and that's a degeneracy for multiplet. So you can think of D as counting the number of BPS multiplets rather than states. Okay, and it turns out that there's a kind of I think a magical result due to Dijkgraaf-Berlin in 1996, where they proposed that a particular modular Siegel modular form, which is well known in the number theory literature. It's called 510. It's a Gusa-Cusp form. And they proposed that, so 1996 is when this result came. So it was about 6 months after the famous Strominger-Waffa result, where they actually reproduce the black hole degeneracy of black hole. They did a microscopic of degeneracy of black holes, which matched the entropy computation. And so this was really the first example in 4 dimensions where they actually got it right. Again, that would be in the limit of large charges. So N, L, and M should be large charges. And some definitions here. Q is e power 2 pi I tau. R is e power 2 pi I z. And S is e power 2 pi I tau prime. Okay. So the Z capital boldface Z is actually a symmetric 2 by 2 matrix with entries tau, Z, and tau prime. Okay, so from the StatMech viewpoint, Q, R, and S are fugacities for the charges N, L, and M. Okay, so this was a miraculous. I mean, I don't know how they even wrote this thing. They just showed that it worked, and it took many years, probably more than a decade, for somebody to actually derive this formula, and that was done by Justin David and Ashok Sen, at least a physical derivation. So there are other quarter BPS states. You can count in other n equal to 4 states. So that's actually a family of Zn orbifolds. These are called the CHL orbifolds. I'll focus on simple Zn orbifolds of type 2 strings on K3 cross T2. And they still, so these are asymmetric orbifolds and they preserve supersymmetry. Sometimes orbifolds break supersymmetry. They preserve this thing, but what they do is they reduce here these 6 and 22 are related to the number of vector multiplets. And so what will happen is it doesn't touch the 6, but it reduces 22 to some smaller number. And so the T-duality group becomes smaller and the number of charges come down. A precise number is not important, but okay. So yeah, that's what I'm saying. Electric and magnetic charges in these theories are objects which are valued in a lattice of signature 6, P of n, where for at least I can write, I mean, we know formulae for all n. I should mention this restriction, n1, 2, 3 to 8 is if you pick G to be a symplectic automorphism. And so then there's a theorem of Mukai which says that it can have only up to order 8. And it says that the order fixes some property of it. Okay, so you know this P of n, I'm just giving it for prime cases, but we know the answers for everything. Okay, so SO6PNZ is the T-duality group and gamma 1n. So the S-duality group also reduces to a subgroup of SL2Z. Okay, level n. So this n is the same out here. But the generating function of BPS states again takes a similar form. And so This now is also a Siegel modular form, but now of a subgroup of sp4z. And electric charges are now fractions, and their fractions can be 1 upon n. Okay, so we account for that. So a little n will continue to be integral for us. Okay, even though the actual electric charge is fractional. Okay, and so for these examples, for prime cases, it was done by Jatkar and Sen, and then my student Krishna, then student and myself, we completed the story for the non-composite cases, and there's much detailed discussion many years later by Pearson and Borcherds. Okay, so this is the setting. So we have a bunch of modular forms associated with this Zn or before. So there are 8 of them if you wish, and they count. So the funny story, which actually again goes back to Dijkgraaf, Verlinde, and Verlinde, what they showed was that you take this phi 10 and take its square root, and that's also a Siegel modular form with integral coefficients. In general, that need not happen, but phi 10 has some evenness properties, which says that the square root gives you another Siegel modular form with integer entries. So this is the general prescription. You just take the square root of any of those 8 guys and ask, do we get something sensible? And it turns out that it is sensible only for n equal to 1, 2, 3, 4, 5, and 6. And so then you get, so the symbol delta, I'm hiding the weights or whatever. I'll define all these quantities for you later. For n equal to 1, 2, 3, and 4, the square root is something called, again, I'll explain all these terms, the Wildcats, Borcherds, WKB. It's not like the WKB approximation in this talk. It refers to a denominator formula for a family of, again, a big word, Borcherds-Kac-Moody algebras, and superalgebras. I will not dwell too much on the super aspect of it. And again, this is known from the work of Gritsenko and Nikulin, but the connections for n equal to 1 goes back to DVB, and for 2, 3 is due to Cheng and Dabolkar, and 4 was due to Krishna, due to me and my student at that time. And these are Borcherds extensions of some Kac-Moody Lie algebras. Again, I'll explain what is meant by a Borcherds extension of some Lie algebras. So there's a construction of Lie algebras starting from something called a Cartan matrix. Again, we'll see how this is constructed, that are associated with certain rank 3 Cartan matrices AN. And the real thing is that it's not known whether there's a Lie algebra associated with the square roots for n equal to 5 and 6. Okay. And actually, there's a beautiful result due to Cheng and Verlinde, who first showed it for delta phi, which is a square root of phi 10. They showed that there is something called a Weil chamber in Lie algebras, and it has walls. And so they showed that the walls of the Weil chamber are walls of marginal stability. So quarter BPS states are interesting. Their degeneracy is not a number, even though I wrote something as if it's a fixed number, well-known number. This number can jump across walls. So you have to be in some chamber for it to, this number can jump, and the jump is interesting. What happens is that this gets contribution. So let's focus in terms of large charges. So for large charges, there are 2 kinds of black holes which can contribute significantly. And this is very special to n equal to 4. N equal to 2 onwards, it's more complicated. That there are single-centered black holes and 2-centered black holes. So 3, 4, they don't contribute. They're not relevant. They're very, very sub-leading, exponentially suppressed. So what happens is that 2-centered black holes will be stable on one side of the wall and will be unstable on the other side of the wall. So this degeneracy, the jump in the degeneracy will be equal to the degeneracy of the loss in the degeneracy of the 2-centered black hole. Okay, these are supersymmetric black holes. Okay, and so this DNLM is not truly a fixed number in that sense. It depends on a choice of Weil chamber. Okay, so it's very strange that 2 different kinds of walls get mapped to each other, and every wall is related to something called a simple root of the Lie algebra. Okay, so this talk, so coming back to this, it's not known whether there's a Lie algebra associated with the square roots for n equal to 5 and 6, but from the physics viewpoint, we know the walls of marginal stability. Okay, so we are able to say what, I mean, if you give me the walls of marginal stability, I can get this sort of a matrix. And there's also a no-go theorem due to Glitz and Nicolin, which implies that they cannot be known objects like VK and V superalgebras. Again, this is something I will define. Okay, so these Cartan matrices are obtained from the walls of marginal stability, and this is mostly due to Ashok-Sen. And but of course, the actual computations, maybe we did it later. But so for A1, it's a rank 3. It's a 3 by 3 matrix. There are 3 roots, and that's it. But in this case, there are 4 simple roots, but this has a 0. This has a 0 eigenvalue, and this has 6, and there are 2 0 eigenvalues. You can check. But A4, A5, and A6, all of them now they have infinite. They have infinite roots. Okay, the walls are infinite. A4, and there is some structure which changes from A4 to A6, and let's go back. So there's a nice formula which captures everything, which is for n equal to 1, 2, 3, 4, and 5, and 6. You just take this quadratic equation, plug in your value of n, you will get 2 values of lambda, pick any one of the lambdas, and you plug it in there, and lo and behold, you get the Cartan matrix. So you can, it's a nice exercise to check. Tricky fellow is actually A4, where you need to take a limiting case. Okay, so this is the setup, and so the question which we are trying to answer is: are there for 5 and 6, is there a Lie algebra? If it is there, what is it? What kind of Lie algebra is it? Okay, so this is, I'll stop here and pause for questions, comments.
Suresh, I have a question here.
Yes, yes,
So this Lie algebra structure, is it known for the twisted twining?
Yes. Yeah. Twisted twining, etc. I will show you a particular graph and show you the twisted and twining and etc. I will discuss that. Yes, it is known for all of them. Yes.
Hi Suresh, a quick question.
Yes.
Why SP4? I didn't quite catch that. Why SP4?
Why SP4? Okay. So we don't know why. Okay, but the point is that there are 3 charges, and they combine to form this Z. And the Siegel modular form, this is just upper half space. That's it. Okay. So I don't know a deep reason how. It just happened to be, So actually, Atish, I think, had some M theoretic interpretation of this, etc. But everything I feel is hand waving. It's just what we have is we have just cooked up, and in some sense, the best derivation is the work of Ashok Sen and Justin David, where they actually obtained this object, and that's about it. Okay. So all I can say is these spaces there are 3 charges, and this is also 3-dimensional. So the fugacities are also 3-dimensional. Okay.
Thanks.
So Z is upper half space, and SP4Z has a natural action on it. So in my notation, SP2Z is SL2Z. Any other questions? Okay. So now we will go into a mathematical introduction, and the mathematicians shouldn't get upset because I'm going to be very, very low bro, and physicists will find it too high bro. I think I'll fail in both fronts, but okay. So first thing is I'll just define modular forms. You're not going to learn about modular forms from this talk, but at least some definition. Okay, so a modular form f of tau of weight k is a function of the upper half plane, so im tau greater than 0, such that you make this kind of A, B, C, D belongs to SL2Z. So A, B, C, and D are integers, and it transforms such that this C tau with up to this factor C tau plus D power k f of tau. So it goes back to itself. So what you have to do in this, what I have in mind is that there's a torus whose complex structure parameter is this tau. Okay, so you should picture a torus, and so these, for instance, these appear naturally in computing chiral partition functions in CFTs on a torus with modular parameter tau. Okay, so for instance, I'm doing this computation. Anybody who has quantized boson in 2 dimensions will know this, that there's an oscillator part and there's a 0 mode part for compact things. Okay, so, or the momentum part, the momentum and winding part, we ignore that. And there are oscillator modes. These are the non-zero modes. for 24 chiral bosons. So for one chiral boson, so what you find is if you do this trace q power L0 minus C upon 24, so what you get is C is 24 for 24 chiral boson, so it becomes L0 minus 1. And so the leading term will, so you start with the 1 by q and you get a nice thing which is the inverse power of eta of tau power 24. Okay, and this, remember, is the same object which was the generating function of half BPS degeneracies of electrically charged black holes. And remember, I told you that there was a duality which mapped it to the states of the heterotic string, where one, the supersymmetric side is kept in the ground state, and that is a bosonic sector in the heterotic thing, and you just get contribution from oscillator modes. So this kind of gives an intuitive but explanation for this thing. And so the 24th power of eta, but eta of tau itself, the Dedekind eta function, is a right half modular form, but not of SP SL2Z or PSL2Z, but of a subgroup. If you want to write it properly, then eta of tau will have some phase which will be a 24th root of unity. That's allowed. So coming back to this definition, we can allow phases, and so those are called characters, and those phases will be a 24th root of unity if you want to write it. So when you take the 24th power, the phase goes away. Now, Jacobi forms are two variable generalization of a modular form. So remember here we had a case of taking a torus. Now suppose you have a point on it and you ask under gamma, which belongs to a PSL2Z tau, we know goes this way. It's actually a very nice exercise to prove this, that Z goes to Z upon C tau plus T. Okay, so first thing is, so Jacobi is a function G of tau and Z, or Z of weight K and index M, which transforms as follows. So first focus on the weight part. So under modular transformations, so I've written it in a reverse form, but doesn't matter. So it says that the C tau plus D goes with a K, but there's also a phase which is M dependent, which is the index dependent. So it goes, so this object is equal to this. That's what it says. So it's kind of what I did. It's like if I took here and wrote this as saying C tau plus D power minus K times F of this object equal to F of tau. It's called a slash operation in the math literature. Okay, so that just, so ignore all these things, this definition. It just says that this is equal to this. But that's not it. Z is a point on a torus. So if you transform, if you go, you think of this torus as complex plane modded by, Z plus Z tau, and then you will see that Z and Z plus 1 are the same point, and Z plus Z tau are the same point. So in general, you will have these elliptic transformations, and what it says is that G of tau Z, so now tau does, nothing happens to tau, but just Z is going to its images. And that again gets this sort of a phase factor to itself. Okay. So now the thing is, you might ask, how on earth did someone come up with this weird definition? And so, okay, so, but let's do an example again. So the Jacobi theta functions are Jacobi forms of weight half and index half of a suitable subgroup of SL2Z. We'll focus on one particular guy, theta 1 of tau and Z. It's a sum over L belonging to Z. And that's an e power I pi L. So you can see that you can break this up into positive terms, positive and negative coefficients, with L being even and odd. So it is like A minus B, where A gets contributions from L even and B gets contributions from L odd. Okay, so you can just, so this is just a definition. So this is a nice example. Siegel modular forms are, again, they're functions of point in upper half space. So what is this upper half space? It's tau and tau prime are like similar. Im tau should be greater than 0. Im tau prime should be greater than 0. But there's a slightly more complicated thing, which is that imaginary part of tau tau prime minus z square, which is the determinant of this, should also be greater than 0. But these are the properties which define a genus 2 surface. Okay, and how does the sp4 matrix, sp4z matrix act on this Z? It acts like Z goes to M times Z. Now these are all, remember, A, B, C, D are 2 by 2 matrices, so order matters. So M dot Z means first, this is the matrix A plus AZ plus B times CZ plus D inverse. Okay, that's how it transforms. And so it generalizes, in some sense, it generalizes this transformation. But here there was no ordering issues. We could have written it as, C tau plus B inverse times A tau plus B, or the other way around, nothing would have mattered. Okay, so it generalizes that. But a Siegel modular form of weight K is a function of this Z, which has this transformation property. Now, again, we want a number, so you take det of Cz plus D power K. Okay. So now, if you're given this object, then you can ask, can we do some expansions, etc. So tau prime tending to I infinity, which is S going to 0, you obtain what is called the Fourier Jacobi series. And the reason for this statement, and if you look here, the coefficients, so we have pulled out the dependence on S or tau prime. And so now what remains is tau and Z. So what we get are coefficients which are Jacobi forms of weight K and index M. Okay, so what is very interesting is that even if you didn't know what a Jacobi form was, if you try to do this expansion and try to study the subgroup of SP4Z, which preserves the cusp at infinity or preserves the point S equal to 0, lo and behold, you would recover these two transformations, which is very, very, very cute that you would see the elliptic and the modular things happen. Okay. So now the Igusa cusp form, which we saw already for as a generating function of quarter BPS rate, it has weight 10, and it's leading for, so I wrote here M should be greater than or equal to 0, but that this particular guy doesn't have a 0 term. The first term is something which is called phi 10 1, and that has a nice thing in terms of the two objects that we already saw, theta 1 square, eta of tau power 18. So you can go back and check that in terms of weights, theta 1 has half, eta also has half, so this becomes half into 20, which is 10. Index comes only from the theta, which should have a Z dependence, theta doesn't. So theta 1 has index half and it doubles, so 2 times half is more. Okay, so, and there's a mathematical construction which says that if you know this guy, and it's called the additive lift, then you can write the whole thing. Okay, so this is just these are the objects which come. Again, there's going to be a short introduction to Mathieu moonshine, and it's really short, nothing explicit, but I just need one small object. It's called a class function for a finite group. Okay, so function f from finite group to C is a class function if it is constant on a conjugacy class. That means f, so let G and H belong to the finite group. So if you just conjugate by elements in H, it doesn't change. So it depends, it's only depends on the conjugacy class of G. Now let V be a G module or a representation of G, need not be reducible. Here it is okay. Let V be a G module corresponding to an irreducible representation R of G. Then chi R is nothing but trace V of G. And this is a well-known, this is a classic example of a class function character. Okay. So let R1, R2 up to Rs denote all irreps of G. Because I have finite groups, the number of irreps are also finite, so I'm okay. I mean, we can define class functions even for continuous groups, but that's not what I want. Okay, so then for a class, this very important theorem, it says that if you give me any class function f of G, that can be expanded in terms of the characters. So these chi R1 to chi Rs provide a basis, and you get coefficients AI. If V is a reducible G module, then trace V on that G will be a class function, of course, for the same reason this was. But now there will be coefficients which will be integral and tell you the multiplicity of their. So if you have 5 times chi R2, that means the representation R2 appears 5 times. So additional condition comes when it is coming from some real module is that AIs are integers or positive integers, non-negative integers is probably the correct statement. Okay, so this is something which we have. So what I'm going to do is I'm going to phrase moonshine, Mathieu moonshine, as giving you class functions for conjugacy classes for a group, which we call the Mathieu group M24. Okay, so it was discovered around 1861 by Mathieu. Mathieu was a mathematical physicist, so people did not believe that there could be these sporadic simple groups. And it took him many, many decades to convince the mathematical community that this group exists. He found not just M24, he found a few more. Okay, so M23, M12, M11. so on and so forth. M12. Okay, so we found a few more of those. So, but the key point here is this 24 has some meaning here. M24 can be related, it's a subgroup of the permutation group acting on 24. So it's M24 is a subgroup of S24. And it has 26 irreps and 26 conjugacy classes. So for any permutation group, it is known that conjugacy classes are given by cycle shapes. So you look at some element and you just say, you know, it permutes things, right? So you say if 1 goes to 3, goes to 4, comes back to 1, so that's like a 3 cycle. So any conjugacy class will be, there's one invariant of it which says that there are A1 1 cycles, A2 2 cycles, A3 3 cycles, AN n cycles. So for Sn, that's what you will get. And in this case, it's S24, this summation should be 24, of course. So n cannot exceed 24, obviously. Okay, so Conway and Norton asked, they asked, what are the conjugacy classes of S24 that reduce to M24? That means they found that all the conjugacy classes of M24 have balanced cycle shapes. I'll explain what that is. But of course, not all balanced cycle shapes of S24 are M24 conjugate. There are more than 26, okay. But there are 26 of them are this. So a cycle shape rho, which is like this, said to be balanced if there exists a positive integer m called the balancing factor, such that rho is equal to m by, so what I'm doing is you're inverting. So you're taking this guy, replacing this n by m by n, 1 by m by 1, so on and so forth, but keeping these things. So if it goes to itself. So here's an example. Rho is 1 power 8, 2 power 8. So first thing we have to check is it 24? 8 into 1 is 8 plus 16, 24. So that holds. So it makes sense. And it's balanced with m equal to 2. Okay. So balancing means really it says, this leading this fellow should be equal to this should be equal to this, so on and so forth. There is some symmetry in the problem. But if you take a 2 power 12, it has only one term, but it's balanced with m equal to 4. But you can look at something like, 1 power, some vague thing like 1 power 10, 2 power 6, say, 2 power 7. That will, that is a valid permutation, conjugacy class for S24, but it's not balanced. So it cannot be conjugacy class for M24. So here's so what is moonshine? Moonshine is actually a relationship between sporadic simple groups and nice objects, modular forms, Siegel modular forms, Jacobi forms, Lie algebras. These are the kind of things. So this theorem goes back to 1985. To every conjugacy class of M24 that exists a multiplicative modular form, eta rho of tau, given by this map. Okay, so rho is say 1 power a1, 2 power a1, n power a1. So you look at this product, which says that eta rho of tau, which is just a product of Dedekind eta function scaled by j. So this is just a nice formula. Okay, but turns out that this particular combination has magical properties. It has something called multiplicative. So it says that, for instance, if you look at a mnth coefficient, that's equal to am an if m and n are co-prime. And if you look at the cycle shape 1 power 24, that just gives you delta of tau, which is eta of tau per 24, which was the generating function of half BPS states. Now comes this very interesting point, which was made by, we connected this with the half BPS states in type 2 string serial case. So eta rho of tau, what it says is that you do a refined counting of the generating function of half BPS states. You look for G invariant states, and where G is any element of M24. And then you will get, lo and behold, you will get eta rho of tau. Okay. And so the punchline, the moonshine statement is there exists a M24 class function which evaluates to eta rho of tau for conjugacy, for all conjugacy, sorry, spelling mistake here, rho of M24. Is this, are there any questions here? So in this case, what we are getting is modular forms, which count half BPS states, if you wish, refined half BPS states, which are given by this. So this is Mathieu moonshine in physics.
Suresh, I have a question here.
Yeah.
So there are these 24 conjugacy classes. So you get
26.
Yeah. So you get 26 eta rho.
Yeah.
So all these 26, you can interpret them as some refined partition functions for how.
Yeah. So it's a little bit complicated in the sense that not all of them are realized as symmetries in an easy fashion. So all of M, so the real catch is that M24, there is no point in the moduli space of type 2 on K3 cross T2 where M24 is a full symmetry group. So there are, but you could find some particular point where some of them are, something is a symmetry, etc. But the cleanest ones are when G is a symplectic automorphism, but that's only 8 of them.
Okay. So for the 8 of them, you certainly have the interpretation. For the
others, few more there is, others it's little bit more this thing. So yeah, that's a very nice question.
Hello, Suresh, just a follow-up to that question. So that means that one doesn't actually know in any picture the states, which
that's because the BP the Hilbert space is much bigger than the BPS states, and so it looks like it's not a symmetry of the physical theory. I mean, M24 isn't. Okay, and if you look at symplectic auto, so for instance, Gabardiel and collaborators, they tried to look for various possibilities, adding quantum symmetries which are not symplectic, etc. And they have got a few more now. I don't remember if everything comes that way. Okay. So some of them will come in one region in moduli space, some of them will come in a different region in moduli space.
Yeah, so just to make sure, so it's not like we can kind of count the states explicitly and write down in any picture explicitly the states to get these eta rows.
No, you can. I mean, like I said, if you pick one, if you give me one of these rows, yeah, if I can find a point in the moduli space where it is, then I can do the count by using the connection with the states of the heterogeneous. Yeah. So, but I need to know where in the moduli space.
Okay. Okay.
What I'm unsure is, are all 26 coming this way? Now I should know, but I've forgotten. Okay.
I mean, so there's actually, I mean, the question is whether there's actually a explicit vector space on which M24.
Yeah. So no.
Even
there's a mythical space. There's a mythical space, but no, there isn't.
Even if you have to throw out some physical non-BPS states and so on and so forth.
Yeah. See, half BPS are the cleanest in some ways, and there's no jumping and etc. But what I'm saying is that if you look at the full space of physical states, they don't see M24. I mean, when we are looking at type 2A on K3 cross T2, we are looking not at just only the BPS subspace or something. Doesn't seem to be a very nice subspace.
Okay, thanks.
So that's so Eguchi, Oguri, Tachikawa in 2010, they actually had this beautiful paper, and they showed that there's also connection with mock modular forms, but I think I'm going to state it in a very, very simple, practical. Excuse me. Okay, so the thing here is that there exists a class function that associates a weight 0 index 1 Jacobi form to each conjugacy class of M24. So what Eguchi, Oguri, Tachikawa did is they looked at the simple case of psi 01, which is the elliptic genus of K3, and what they found was that the initial coefficient, if you expand it in terms of there is some SL2 hat, a fine subalgebra of n equal to, actually in terms of characters of n equal to 4 SCA, they found that, lo and behold, out of the blue, they found that the dimensions of representations of M24 started coming. And so they had some guesses looking at the first few terms. And I don't know, I got some message. Participants can now see your presentation. I mean, were you able to see everything so far?
Yeah, I think everything was visible.
Okay, good. Okay, sorry. But then, for instance, at order 6, I think Q power 6, they got, there were 2 possibilities and they chose the wrong one, but then you can fix it. It was fixed by others. So, but what happens is that, so the twisted, actually I should call it the twined elliptic genera are Jacobi forms at level M, where M is the balancing. So these are subgroups. And at each level, the space of Jacobi form is of some finite dimension. And for instance, for prime levels, it's 2-dimensional. In other words, the first few terms in the character expansion uniquely determines the Jacobi form, and the rest of the terms provide validation. So using this idea, Jacobi forms were determined for all 26 conjugacy classes of M24. So it's a long work, actually. Cheng corrected the Q power 6. Gabardiel et al. I just wrote one paper, but they wrote several papers. So did Eguchi and Hikami. So Gabardiel et al. And Eguchi, Hikami et al. Hikami, they completed the story. And actually, so then you want to ask, is there a class function? So you write it in terms of characters. And Eguchi and Hikami actually carried out to Q power 1000. I mean, this is to the fourth. And in 2012, Terry Cannon proved that such a class function exists to all orders if it is verified to order Q power 400. So Q 1000 is greater than 400. This is probably one of the most non-constructive proofs of the thing. And this is something which is still true about Mathieu moonshine, is that we do not have, some nice vertex algebra construction. I mean, the kind of things Loga was asking. We don't have that. We just have, some thing which some mathematical consistency. That's it. Okay, this doesn't mean anything. I mean, Terry's proof is beautiful, but it's non-constructive. So the weird thing is that before Eguchi et al., my student Gopala and myself, we actually had we were trying to write a conjecture for quarter BPS states. So let me just try to say what it is, and let n denote the order of an element G in M24, and rho is the conjugacy class of that. To every M24 conjugacy class, there exists a Siegel modular form phi rho of Z at level n subgroup of suitable weight. And there exists a class function that generates all these modular forms. Okay. In 2009, we were actually only focusing quite a lot on the symplectic automorphisms. So that was our thing. And so for rho equal to 1 power 24, which is the identity of 1 obtains phi 10, the generating function of quarter BPS states in type 2 on K3 cross 2. Okay, so for other conjugacy classes, the Siegel modular form is the generating function of G invariant or twinned by the element G quarter BPS states. And the proof is actually carried out in a case by case. And it took many, many, many years to complete the story. So I'm just kind of presenting it in a linear fashion. But Pearson and Volpato, and much more recently, like last year, I think, or 2020, I think, my student and I actually gave some proofs of this fact that these are Siegel modular forms. But actually, what I showed was that this particular moonshine involving the Siegel modular form unites the other two examples. There were two class functions, one involving eta products and another involving Jacobi form, and they get unified by the Siegel modular form. But what is very important is a byproduct of this is that that's a product formula for all the Siegel modular forms. So there are these phi's, and we actually have a form of writing it as a product. Okay. So let me just pause here and say that what we have is, if you give me a conjugacy class of M24, you get an eta product, you get a Siegel modular form, you get a Jacobi form. And each of these are class functions. So this is the, again, I'll pause here for any questions. Okay, so
one
finally, I'm going to give you a practical introduction to BKM Lie Algebras. And during my students' thesis defense many, many years ago, I think 2010, I guess, or 2011, Sunil Mukhi asked for a very, very simple example of a BKM Lie Lie algebra. And we were giving very, very complicated examples. Today, I know better, so I'm going to give you a very, very simple introduction. So first thing, let's understand what Kac-Moody algebras are. Okay, so here the idea is that so the generators of the Lie algebra can be decomposed, the usual Cartan-Weil decomposition, into H, which is the Cartan subalgebra, and R plus and R minus, which are positive and negative roots. The simple roots, so if it's a rank R algebra, there'll be some 1, 2, 3, 4 up to R. They will provide a basis for R plus, and the root lattice is just taking these think of these as some, actually think of alphas as some vectors in some r-dimensional space, and you take all integer coefficients in front of them, you get a lattice. Okay, so the Lie algebra in this Chevalier basis is H is commute, but here's the one, H alpha, E alpha j is Aij A alpha. So this is the first appearance of the Cartan matrix, which you write it as the matrix of this thing. So this, in this example, would be an R by R matrix, and E alpha I, E minus alpha I is H alpha I. Okay, so the elements of R plus are generated by taking multiple commutators or Lie brackets of the simple roots subject to the said relations. So if you're given this Cartan matrix, it says an Aij for j not equal to I has to be negative. Okay, so 1 minus Aij will be some number of times, that should be 0. So this in some sense defines a Lie algebra for you. It says, so you can turn it around, given a Cartan matrix, okay, then you look for roots whose inner product gives this Cartan matrix, and from that you can write the Lie algebra, but you have to go ahead and find out what R plus is by imposing set relations. So this I'll call G of A. Okay, that means that the Kac-Moody Lie algebra, which you do by starting from this Lie algebra in the Chevalier basis and impose set relations. Okay. So some properties of Cartan matrices, they are typically symmetric. We will only consider it symmetric with 2 on the diagonals. Okay. Again, we are looking at only, we'll relax this condition in a moment. 2 on the diagonals, and third is negative or 0 entries for off diagonal terms, such that Aij equal to 0 implies Aji equal to 0. Okay. So this is true only for, I mean, I'm assuming when it's not symmetric, only this kind of condition. And the Cartan matrix is obtained from as an inner product on the alpha i's, which are living in the dual of the Cartan. So it is just something like this. So you can see if you have, if all your simple roots have norm 2, this 2 will cancel with the denominator. It's just the inner product of alpha I, alpha j. So for every simple root, real simple root, you can define a reflection, okay, which acts like this. So it is just like taking a vector and projecting its component onto alpha and inverting that and doing that. That's what this is doing. So beta alpha, this is just picking out the component of beta along alpha and switching the sign. So 2 times alpha I will switch the sign. Okay, so Si of alpha I, if you just look, it takes the root 2 minus itself. The Weyl group of a Lie algebra is just defined to be the group generated by all Weyl reflections. Okay, so I need some definitions more. So there is something called a Weyl character formula, which tells you what the character of any representation is, highest weight representations, for instance. And but the one ingredient there is a Weyl vector, and in your standard course in SUN, etc., rho will be written as half of the sum of all the roots, simple root, positive simple roots. Is that correct? Or simple roots? Yeah. But what we will do is we will work with rho alpha. Rho is the sum vector, which has whose inner product is the following with a minus sign. Minus sign has got to do with Borcherds convention for some other reasons. Don't worry about that. Usually it's written as plus, so you can just take this. What is in your standard books called rho is minus rho for me. Okay, for all simple roots. And then it's easy to see that if you take any rho and if you do SI of rho on rho, it just gives you back alpha I, which is an element of R plus. More generally, for any W belonging to this, one has SI of rho minus rho belongs to R plus. So the Wildcats denominator formula is actually a very interesting thing. It is a summation of some objects equal to a product of something. Okay, so let's look at the left-hand side. Left-hand side is summation over the Weyl group. And determinant of W is, is just this, det W is plus or minus 1, depending on whether you have even number of, how the element W is constructed, whether it's constructed with even number of elementary reflections or odd number. Okay, and W acting on this. So that is the sum side. Product side is a product over all the positive roots with 1 minus e power minus alpha times the multiplicity of alpha. So you can have positive roots which have the same weight, but they could be I mean, they can occur different ways. So the left-hand side knows about the simple roots because simple roots, their Weyl reflections generate the Weyl, as they generate the Weyl group. Right-hand side provide details of the space of all roots. Okay. In a general situation, the hardest part of the story is to get the multiplicity of roots. Okay. And so as the algebras become more and more complicated, not finite examples which we know for semi-simple Lie algebras, that's all very easy. But once you go to affine itself, that the answer becomes pretty hard. And the answer is known by connecting this denominator formula to Jacobi forms. Okay. So from your viewpoint, just the thing to take away from here is that the denominator formula, whatever it is, it's summation equal to product. One side is a Weyl sum or Weyl roots, and the other is a product over the positive roots. So let's do examples now. Okay, the SU3 or SL3 Lie algebra, it has two simple roots, call them alpha 1, alpha 2. And the Cartan matrix is just 2 minus 1 minus 1, 2. Set of positive roots here is alpha 1, alpha 2, and alpha 1 plus alpha 2. So where E alpha 1 plus alpha 2 is, just take E alpha 1, that's commutator or D bracket with E alpha. And the SER relation tells you that there are no more. It stops here. So here's an example where it's over, the process end. And the Weyl group is S3, which you can see is just, generated by the Weyl reflection S1, S2. So S1 square is 1, S2 square is 1, S1, S2 cubed is 1. And rho is again half of the sum of the the roots, simple roots. So it's just half alpha 1 plus alpha 2. And this minus is my stupid convention. Okay. So now you can just go ahead and you can write out the product thing. The multiplicity is simple here. It's 1, 1, then 1. You just go ahead and expand it, and you'll, lo and behold, you'll find that you can write it as this. So pi, which is this product form, if you expand it, it looks like there'll be 8 terms, but there's some cancellations, and you get exactly 6 terms, 3 positive and 3 negative, and which is agreed with. So here, the way I've written it, I think these are all the positive sign guys. These are all the negative guys. Okay. You can ask me why there is no S1, S2, S1. You can check that that's equal to this. So the proof that the sum equals product is very, very trivial to check here. It's just some algebraic manipulation which anyone can get. Now let's get on to SL2 hat. It has 2 simple roots, call them alpha 1, alpha 2. And the Cartan matrix now is 2 minus 2 minus 2. Okay, so the only change here is minus 1 got replaced by minus 2. But now, if you see here, this guy has 0 determinant, and the root delta, which is alpha 1 plus alpha 2, has 0 norm. So it's imaginary. By the way, in Lie algebra, the norm is actually what we call norm square in physics. So it has 0 norm, and it's as such roots are called 0 or negative number. Those are called imaginary roots. So there is an imaginary root, but it is not. It's not a simple root because it's a sum of alpha 1. So the set of positive roots, which I will write out now and explain, now includes imaginary roots. One has. So these are all, these 2 guys are now normal. There are infinite of them, of course. But there is m delta. So you can see there's 1 delta, 2 delta, 3 delta, 1 of each. So now you can just go ahead and write the product side of the Wildcats determinant formula by looking at this. Okay, pi is e power minus rho. Alpha belongs to R plus into 1. So you will, lo and behold, you will get this. It will be an infinite product, doesn't matter. But then, if you look at it, what you get is, don't worry also about this s power half. I'm just putting it for some reason, but it's just theta 1, the same Jacobi form that we saw. It has, there's a famous identity due to Jacobi. It's a triple product identity. And this is what. So McDonald's actually reverse engineered the whole thing. He said that, look, if I know for theta 1 that this is, so the sum side of theta 1 is exactly what we wrote before, but it has a product form, and that forces you to include this. So this term is this. Okay, so this is the first use of automorphic form. And one can of course show that the sum side is exactly sum equal to W belonging to the while group of SL2 hat. And that will have this form. And what I want to point out here is that the while group is a Z2 semi-direct Z. So you can break this up into, like I mentioned, even and odd terms. And so the even guys will be one of the Z2 and the minus sign. So the others, and the Z will be the sum over this. So that's how you break it up and write it as sum over integers. And now you see here that showing that this is equal to this is not simple. So you're showing sigma equal to pi is a non-trivial identity involving Jacobi forms. And the use of Jacobi forms for affine Lie algebras was pioneered by McDonald, who observed the need to modify the product side. Okay, so Borcherds now, so far we had imaginary roots, but these were not simple. Borcherds asked, can we add, add imaginary simple roots to Kac-Moody algebras? So imaginary roots have norm or norm square less than or equal to 0. Now, if you add these guys, the diagonal elements in the Cartan matrix now are not, can also have 0 negative entries. And what he showed was that there's a particular modification. So remember, McDonald's modification happened on the product side. The Borcherds modification happens on the sum side. And these contributions are the contributions in red are the contributions for the imaginary simples. Okay, I won't explain this in details. So what Borcherds did was that how do we make this work? You add enough imaginary roots such that the above sum or product becomes a suitable modular form delta, the automorphic correction. Okay, and so the product formulae which he derived for these things are called Borchert products, and they lead to an explicit determination of root multiplicity. So let's now do a simple example of a BKM Lie algebra. Consider the addition of the following set of imaginary roots to SL2 hat. M distinct bosonic simple roots of weight delta 2 delta. So there's already one delta which is not a simple root, but to that you add M extra roots with the same weight, but they are now simple. Now the relevant Jacobi form is theta 1, but for every one of these M's I put a eta of tau power M. So now I get a Jacobi form, and eta as a product formula, theta 1s. So the lo and behold, we get the product side. Now the Borcherds correction term really is of this form. You have to write this and write it as a summation, but I'm not going to do that here. But I am just saying that the term in red here, I'm just calling it T, and T is just the rewriting this as a sum. Okay, so for if you write for M equal to 24, the sum involves something called the Ramanujan numbers, tau of n. Okay, if you write this as a Q series, and we will denote this BKM. So this is now a Borcherds this thing, and this is a Wildcat. So you can prove that sigma equal to pi more or less. It's not very hard once you assume the SL2 hat formula. Then we'll call this as B Borcherd extension of SL2 hat with M of this kind of roots. It's an infinite number of imaginary simple roots. Okay. So now we are ready to state our problem. Yeah.
What is the Cartan? Yeah, what is the Cartan? Yeah, what is the Cartan matrix for this?
I can't hear.
I'm asking what is the Cartan matrix of?
Amita?
Yeah, hello. Can you hear me? Can you hear me?
Now I can. It said my internet connection was unstable. Now I think it is back. Okay.
What is the Cartan matrix for this BKM algebra with M extensions?
Oh, it is infinite dimensional, so it will be 2 minus 2 minus 2 minus 2, and then a whole bunch of zeros. M zeros for first delta, then 2. So it's in some infinite dimensional Cartan matrix.
So the upper block is the SL2 hat, and then zeros everywhere.
Yeah, in the diagonal.
And off diagonal terms are non-zero.
No, delta also, it's all 0. It's all zeros because it just happens that alpha 1 with delta is inner product is 0. Delta with delta is also inner product is 0. So it's all zeros.
Okay. Okay. Where is the information about M?
Here.
No. In the Cartan matrix.
That's because it's M times infinity. There are so many of them. It's a number of it's a countable infinity. Okay. I mean, if you want, let's say we just did something very, very trivial. Instead of doing this, we just put M roots of only delta. Okay, then you don't get a modular form, but you'll replace this with 1 minus q power n. This will be theta 1 into 1 minus q power m. That's all. So now in this case, there'll be a 2 by 2 block, and then there will be a m by m block of zeros. So it'll be m plus 2 by m plus 2 Cartan matrix.
Okay, I understand. Yeah,
but it's not a modular object. But it doesn't matter. I mean, here we know the answer. Okay, I'm going to state our problem, but before that, I just want to show you how the square roots work. So deltas are the square roots of phi's. So there are a whole bunch of things. So look at this column. These are the square roots of the genetic function of quarter BPS states in CHL Zn orbifold. So Z1, Z2, Z3, Z4, Z5, Z6. Horizontally you go, there are many, many more, but I'm just stopping at 6 because only that's the square roots work. And so these guys are what are called twining genera or whatever. So these also make sense. So if you go horizontally, what happens is that these have the same Cartan matrix. So the real roots are the same, but they differ in how the imaginary roots come. And that is determined by these cycle shapes. Actually square root here, so 1 power 12 or whatever. So they will all be inequivalent Borcherds extension of G of A1. Same thing. So if you go horizontally, all of them are in that sense. Okay, so delta 3 tilde, delta 2 P1 prime, Q1, all of them have A2, which is just the real simple roots. So in this case, it's a 4 by 4 matrix, but then they differ in how the imaginary roots are added, what kinds of imaginary simples are added. Okay, so that is the thing. But 5 and 6 are not in that category, 5 and 6. But so we don't know, I just added them randomly, rows 5 and 6, because we know these modular forms and they have certain nice properties under the Weil group and other things. So they have all they're set up to be the denominator formula for something. Okay. And we have product formulae for all of them. And this is what we do. We consider family of these 5 Siegel modular forms. 1, 2, 3, 4, 5. You can ask why? Because in some sense, these are the simplest. We could have gone this way. These are uglier and much harder to handle. So these are simpler. So the target here is to understand delta 0, but we want to do it in a uniform way. So we've been looking at all these guys. Okay, and so these are all Siegel modular forms of a bigger group. There is some called gamma n. N equal to 1 will be sp4z, but this is a subgroup of sp4q. Remember, note here that there's an n in 1 by n. But this is a closed group by itself, and it is not commensurate. I mean, it's not a subgroup or anything with gamma 1. It is just some other subgroup of closed subgroup. So this is called a paramodular group at paramodular level n. Oh man, it's a mouthful. N equal to 1, it's just sp4. So if you go ahead and look at the Fourier Jacobi expansion of these guys, this n comes here. So what you see here is that if let's look at m equal to 1 term, okay, that would be a Jacobi form of weight k, but index will be n plus 1. Okay, so for all these examples, we get something very, very nice. We get phi k of half is theta 1 times some power of eta. Okay, so this you can see looks like the denominator formula for some Borcherds extension of SL2 hat. And then if you look at the next term, it has psi 0 n. If you pull out this phi k half, and these are Jacobi forms which occur in something called umbral moonshine. Umbral moonshine is a generalized is a very general setup, of which Mathieu moonshine is a special case. There are 24 examples constructed by Cheng, Duncan, and Harvey. Okay, but what I want to, for us, what is important is that these are well-known objects. So the proposition here, the 5 Siegel modular forms are the denominator formula for extensions of rank 3 Cartan matrices Kn. So in particular, if you look at, like I said, what are the good properties? So Wn be the Weil group generated by the real simple roots with Cartan matrix An. Then for all these guys, under elementary reflections, this flip sign. This is very important. There are a few more properties which you can check. For 1, 2, 3, and 4, actually, they do appear as WKB denominator formula, and in the work of Ditsenko-Nikulin, which precedes all these dyon stuffs. Okay. And our aim is to understand n equal to 5 and 6, but here in this example, sadly, there is nothing for 5 that doesn't appear. And so this is what we wanted to do. And so what we did is we wanted to use an SL2 hat subalgebra to study this denominator formula. Our main result is a decomposition of the two Jacobi forms in terms of characters of the SL2 hat. Actually, phi k half, the wrong statement. Phi k half is just the wild denominator formula for a Borcherds extension of SL2 hat, and psi 0n, we will do this too. So how much time do I have? Or how much time can I take?
Yeah, you can take like 10-15 minutes more.
Okay, okay, good. Okay, so the trick here is, what is this SL2 hat I'm talking about? And this makes use of the particular feature of, so I need to look at the Cartan matrices. Sorry, I have to go back. And I'm not doing it efficiently, it doesn't matter. Okay, so you look here, here's A1, you see that there is a, if you focus on a 2 by 2 block, there's a 2 minus 2 minus 2. This isn't defined, but I can shift here, same here. Okay, and it turns out for all these guys, even these are infinite dimensional, you'll see that any 2 by 2 block, there's a shift symmetry because there is a dihedral group out here. And so you can see that we can embed SL2 hat into this. And so what we do is we embed it and ask, so I don't know the big Lie algebra, but I have a subalgebra of that unknown Lie algebra. Let me ask how do things decompose so that we can track things. Okay, so this is just some definition of SL2 hat. I think I don't need that. Okay, so we would like to embed SL2 hat into a Lie algebra with Cartan matrix. So this is, if you look carefully, this would be a 3 by 3 block inside any of those matrices where n. So you can see if you put n equal to 1, this becomes minus 2. Okay, then it's a 3. So the idea here is we want to look at what are the basic generators. So there's this is E2 should be thought of as E alpha 2, F2 should be thought of F alpha 2. So there's alpha 1 and alpha 2 or whatever, right? So these are three roots. We'll call them alpha 1, alpha 2, and alpha 3, and this is their inner product. Okay, so this is a subalgebra of this big AN, and we want to make some identification with them. So E tensor 1, F tensor 1, F tensor T, and this thing, these are the SL2 hat labels. E2, EF2, E1, F1 are the AN labels. And then we will use so I need a few things. So you start with SL2 or SU2, okay, and then you look at SL2 hat is just you take this and tensor it with what do you call it? Laurent series in auxiliary variable T, okay, and then you add to it a central extension and a derivation. Okay, so D, for those of you who know Kac-Moody algebras from CFT, this is just the Fourier modes of current, which is written J of T, and this would be the central charge, and D would be L0. Okay, so this would be the full Lie algebra, but the Cartan algebra here is three-dimensional. It is H tensor 1, which is just the H of this, and there's K hat and D, and the inner product is off diagonal. K hat and D is minus 1. H is 2. This is the usual killing. Okay, so what we have here is, so there are the Cartan of this 3 by 3 is H1, H2, H3, and we want to go ahead and ask how is the Cartan of this AN related to the Cartan of the SL2 hat, and then lo and behold, you can just go ahead and with these identifications, you get H1 and H2, and then there's just the third thing, you get this combination. H3 is a minus H tensor 1. Okay, so this is how we complete the mapping. It's just more or less unique once you make a choice. So the characters of AN. So first thing is let W hat be the affine Weyl group generated by the reflections by alpha 1 and alpha 2. So we'll just call it W tilde or W hat, I don't know, W tilde. Okay. Now the Weyl group of the Lie algebra is generated by the reflection alpha 3. There are more roots, alpha 4, alpha. For the moment, let's just focus on alpha 3. So that will be the thing which is W hat, and S3 you ought to add. And so if you look at it, that will have a bunch of terms which go like W tilde with S3, S3, W tilde, things don't need to compute. There are a whole bunch of terms. Okay, so, so let's ask that something is the highest weight vector lambda, and for the full AN, and the numerator takes this particular form. T is some combination from, is a placeholder for Borcherds corrections from it. And numerator of 0 is nothing but the sum side of the wild denominator formula. So the numerator, if you just go ahead and use this thing, what you find something that it looks like numerator of rho lambda plus numerator of S3 acting on lambda minus rho, which will become e power minus alpha S3 plus so on and so forth. So you get, so there are many more terms, but this particular term is important because what it does is it connects up with the Fourier Jacobi expansion. So S3 will go with S powers of S. So we will look at the first non-trivial term. And then if you just go ahead and do this computation for this thing, what you find is that numerator tilde is written in terms of some theta functions, and this is what you get. And if you divide by the denominator, you will get characters. Okay. So let's try to understand for A1. So in that case, delta phi is S power phi, 5 half plus 1 plus S psi 01 plus order S square. So the reason here to stop with only this term is because if I took other generators, it will give me higher powers of S. So we are only looking at this particular term. And so we have explicit things. Phi half is theta 1 eta power 9. And psi 01, for once I'm writing a formula for that, but okay, in terms of theta functions. So the denominator formula, so let's look at this term first, of SL2 hat gives a theta 1. Eta power 9 is coming from a Borcherds extension of SL2 hat, and that's what I call B SL2 hat 9. So what, so the thing is, we don't need to consider just SL2 hat, we can do a decomposition in terms of a larger, in terms of this became Lie algebra, B SL2 hat 9. So phi half is the WKB denominator for the Lie algebra. Now, so we have finished this guy. So now we have to ask, what is this? Can we understand this guy? So we want to study delta phi divided by this, but after pulling out the denominator formula. So this we should understand as some bunch of representations of the Lie algebra B. So that's what we do. So let's just call it chi tilde alpha 3. So you just go ahead and you can work out what these characters are by using standard formula. You get something like this. So S times that thing would be F1 of tau and F2 of tau. And so in terms of 3 characters. And there is a symmetry in this problem, which is like an outer automorphism of SL2 hat, which is exchange alpha 1 and alpha 2. Okay, so you would have naively expected 3 functions, but only 2 functions come. And if you look here, it's very interesting. First thing is you see this 1 out here. This 1 here is nothing but the real simple root associated alpha 3. F2 here as a 9 into 1, and this 9 again is exactly the same 9, the same guys that we added. What about these other guys? These are all imaginary simple roots with negative and non-zero now. So what is happening is that the Borcherds corrections not only adds these roots, there are a whole infinite series of these roots. Okay, and these numbers we determined by just putting in, these are known characters. You put it in a computer and you compute these numbers, so you get these things. We went to much higher orders, but it doesn't matter. So this is done in this way. So question is, what are these guys? So we know how psi 01 transforms. We know how chi, actually we don't know how chi tilde, but chi alpha 3, chi without we know how the characters of SL2 hat transform. From that we can work out how F1 and F2 transform. So that's what we did. We actually switched to working with characters of SL2 hat, even though we have this formula. So F and G will differ by this eta powers. Ooh, there's some typo here. So you get G1 and G2, and it turns out that these are vector valued modular forms. What does that mean? G1 and G2, you write it as a column vector, and when you do SL2Z transformations, they mix with each other. So it's a matrix kind of thing. Okay. And so you can, what happens is using their modular transformation, we can fix how G1 and G2 using only few terms that we have indicated above. We can fix them. Okay. But there's some work which is needed to do that. Same thing goes on for AN. We can just go ahead, phi k n half, and then you get now psi 0 n. And so now it's again a Borcherds extension, which is of with this power of eta, which depends on n. Oh, this is not 9, it should be n. I got it right here. And so you can see if you put n equal to 6, something interesting happens, you get a -1. So what the thing is that now it's a so the imaginary root we are adding is fermionic in this case. So be it. But again, that fits in with the, so it's a Lie superalgebra, not a Lie algebra. That's technical. I have hidden the super part of the story out here. So again, we need to decompose the psi 0 n similarly in terms of characters SL2 hat and B SL2 hat, but now with a different extension. Okay. So explicit formulae are available for all of psi of n. So we expand in terms of normalized characters. And so we get vector valued modular form. So n equal to 1, we saw it was only 2 independent guys, 3, 4, 3, and 7. Okay, it becomes fairly large for 6. The modular properties of VVMF follow from the known modular properties of psi 0 n as well as the normalized SL2. So we have actually explicit characterization of vector valued modular forms in this fashion, in addition to their first few Fourier coefficients. But now the question is, can we get closed formulae? I mean, you're not going to, if you want the 100th term, you don't want to sit there and do this by hand solving it. So we got this idea to look at some work due to Gannon, where he constructed this modular matrix differential equation and asked which these VVMS do they solve some differential equation. And what is the inputs for the differential equation? The matrices S and T, that means under tau goes to tau plus 1 and tau goes to -1 upon tau. How these things transform, we can work out. And so you have some R by R matrix. And there's some additional data in the form of an R by R matrix. And this is the one which is hard to determine. And the output is a basis for vector value modular forms of rank R with a given modular property. Okay, the VVMFs that we obtain correspond to one linear combination. And actually, there's a natural choice of basis, and it picks out only one of those guys. But determining this R by R matrix requires the use of a computer. You can't do it just like that. So you need, we know in some sense only one row of the R by R matrix. We need to know R square minus R terms. And for n equal to 6, the dimension of the unknowns became too large, and we were unable to solve for the basis. Surprisingly, we got saved by something. When we expanded the VVMF in terms of suitable theta functions, we got a very, very simple result. I mean, this is something psi 06. Looks like this, and then there is some work of Katz and Peterson which will connect this theta function to the SL2 hat characters, and lo and behold, we got closed formulae which agreed with our independent computation. So that was very, very, very lucky. Okay, so I'm just going to conclude here. So the vector valued modular forms provide explicit formulae for mostly imaginary roots, and they are not all very, very, not necessarily simple. And this is a new result, even though they were known implicitly before. Next, our goal is to organize the Siegel modular forms in the orbits of the full while group. And this result is only a first step. See, the full while group is complicated from A4, A5, A6 onwards because the number of simple real simples is infinite. So the group is very, very large. Okay. But there's a second approach which follows from second quantized umbral moonshine. And this sort of, I mean, I don't know if this exists only in my head, but this enables one to write product formula for the Siegel modular forms. And so at least for so-called A series of the umbral moonshine, Sutapa, my student in this, we actually wrote out the product formulae for these things. And in particular, we can write for explicit formulae for higher coefficients, so S power 2n and other higher powers of n. The key is that they're determined completely in terms of psi 0n. So all the hard work that we have put into determining psi 0n, how it breaks up in terms of the Lie algebras, that so what we are trying at the moment is to exploit this, say, to explain all the other terms in this thing. Okay, and the question, so again, one thing we know, we have the product side. What we don't have is the sum side of the story. So the question here, if you go back to, for any less than or equal to 4, Kritsenko and Nikulin actually show that it fits the Borcherds thing explicitly also. But for n equal to 6, there will be a new kind of correction that goes beyond what Borcherds did and will help us understand the A6 case better. Of course, there are 2 more examples with A5 and A6 that arise from CHL order folds. These are a little bit more messier to handle, but we are still doing that. I mean, it's not impossible. But going back to this Lie algebra, the root lattices for all the examples have the following in common. They are rank 3 Lorentzian lattices with lattice file vector. Such root lattices have been classified by Nikulin. There are 3 kinds of such lattices which differ in the norm of the lattice file vector. So it's elliptic for n equal to 1, 2, and 3. Parabolic where the while vector has 0 norm for n equal to 4 and n equal to 5 and 6 of a hyperbolic type. So the no-go theorem of Kritsenko and Nikulin states that there is no BKM Lie algebra associated with root lattices with lattice while vector of hyperbolic type. So according to them, you should not expect a BKM, but we are already seeing hints of extra terms that are needed, and we have actually classified, looked at some structure in them. And now I'll just finish here with this interesting picture. So these are the walls of marginal stability. So the red ones are the roots which we are talking about. What happens is that there are infinite roots, but all the red roots, they come and they sort of approach this limiting point. So every semicircle here is a real simple root. So there's 1, 2, 3 that I've indicated, but from here to this point, there are infinite of them. And similarly, here, okay, but now starting from half, there are these blue roots, and these are also real simples, and these remain something of a mystery, but they have something strange about them, and these actually determine the correction factors. And if you look at the expansion, character expansion of psi 06, where we do see the blue roots, and that they are sitting as the leading term in G2, and the red roots are sitting in the leading term, at least 2 of the roots. So these and this, and these this and this are sitting in G6. So what we need to do is to understand the Lie algebra implications of the sum side and see if this implies a new kind of Lie algebra. So at this point we have only done the story for psi 0n. How does it extend to the full Siegel modular form? That is the full story, and this is work in progress. Thank you.
Thank you for that wonderful. Like, if people have any questions, you can ask the speaker. I think Ashwin has a question.
Yeah, hi. Thanks, Suresh. Thanks for the really nice talk. So I actually have 2 questions. So one is about this BKM algebra story. So I don't know much the connection to modular forms, but at least for affine Kac-Moody algebras, I know there's a close relationship between like representation theory of quivers and representation theory of Kac-Moody algebras. Does that story extend to these generalized cases? And
okay, good. So so the thing is that there is a nice relationship between the Euler form that you associate with quivers. This is antisymmetric, and Cartan matrices of Lie algebras. So it goes back to the classic. This is this famous work, right? First paper on quivers. Now I'm forgetting the name of the author.
Gabriel, I think.
Gabriel's work, where he showed the affine story connected up nicely with this thing. And so in principle, there will be, I mean, you could, what I would do is every simple root is like a node in a quiver, you know, you could do those kind of things. And Cartan matrix, you could do these things. But the thing is that I don't know if there is any benefit out there. Now, that's one point. Other thing about Borcherds-Kac-Moody algebras, which I forgot to mention, is that they are all, every Borcherds-Kac-Moody algebra that we know is exceptional. So it's like, if you like take the finite case, right? There is the A, B, C, D. These are infinite series, but then you have E6, E7, E8. These are all special there. There's something which has to, come and fix things. So in that sense, similarly, F and G, right? E, F, and G, they are exceptional cases. Every Borcherds algebra, Kac-Moody algebra is exceptional.
I see.
Because you need to find a modular form. So the point, I mean, the thing which has been driving me to look at this is because I mean, in these examples, see, Nicolin and all, they've done some classification, but they don't have any modular form. But lo and behold, hey, I have a modular form, which has all the transformation properties which you properties that you want from a wild denominator formula. So that is the so in that sense, BKM algebras are special.
I see. And my other question is, how much of this story also extends to compactifications with 8 supercharges and 4?
Actually in 2007, when I started working on this problem, I thought I'll work on this problem for 2 years, and for me the holy grail was n equal to 2 compactifications. And okay, but the problem there is the microscopic story is much more complicated, because there is no half BPS, quarter BPS. There's only half BPS. But you can think of small black holes and large black holes. Small black holes are those which have zero area in the Einstein, if you have the Einstein action. So if you try to do the Beckmann-Hawking computation, you get zero area. And okay, so those are the only classifications that we have. But unlike n equal to 4, where only 1-centered and 2-centered black holes contributed, in the n equal to 2 case, all of them contribute. They're all the same codimension. So there is this whole entropy enigma story. So you need to, I mean, I have to think a little bit more carefully about how to do this thing. So, but one of the plans that I have is to look at models which are Z2 orbifolds of K3 cross K2, which break n equal to 4 to n equal to 2. So these are this Borcherds-Kac-Moody manifolds. And in those cases, they are like, they are not true SU3 holonomy, but they're SU2 cross Z2 holonomy manifolds. So maybe there is something nice going on in there, and maybe there is some structure where we can actually make statements about microscopic counting. So this is something which is a wish list for me.
Thank you.
Suresh, I have one question. So in this table that you showed, this with the big matrix.
I call it the periodic table of Kac-Moody algebras.
Yeah. So is there a CHL model realization of the last entry? Is it m equal to 6, n equal to 6?
No.
So this is
actually, this is so all except for this guy, all the others, I know them as as twisted twining.
Yeah, so you see, all the other red ones have twisted twining interpretation except for this last one.
Yeah, exactly.
But okay, but this is just some observation, or it has no implications, or what is the view?
So yeah, I mean, but so I don't know what that means. I mean, the whole story of Umbrel moonshine, except for Mathieu moonshine, all the others are esoteric stuff, mathematical stuff, where there is no, I don't think there are physics models, or actually maybe not that I know of, where they appear. Okay, so yeah, absolutely right, that this particular one does not sit into the twisted twining story. I actually spent quite a bit of time looking through. There's Mason who's classified all the pairs of M24 things. So it's kind of weird that these four, they are like this is like Z2 cross Z2, Z3 cross Z3, Z4 cross Z4. And this I had known in 2012 itself. I had these things, and I didn't check. When Umbrel moonshine came, we checked, and these were exactly fitting that. So there was no Umbrel moonshine when I wrote, when we studied these things. We just did them as twisted twining things. So yeah, but from the Lie algebra viewpoint, I think the way I'm thinking of it is that this is very simple.
Okay,
that's
thanks.
all. Okay, and I have a product formula, and the key is that the product formula, the product formula for all these 5 guys is the same setup, the same. Yeah, someone else was asking something, sorry.
No, I was just asking if there are more questions. Okay, if there are no more questions, let's thank Suresh once again. And
Thank you very much.
Yeah, thanks, Suresh. And we'll see you guys next time.
Thank you. Thank you. Bye.